And assuming here we have figured out the betas, right? After applying maximal likelihood function. And the model can be written as follows, right? Assuming we only have 3 variables. In theory, we can have, many, many variables. We say K variables or, hundreds or even thousands of variables, especially in machine learning, right? In the era of big data, we could have thousands of predictors. But let's say, just in this case, we have 3 independent variables. If you remember the function for mu, right? Mu I is equal to what? Expected rate for y given x is equal to what? In this case, is equal to the exponential of what? X beta, right? And that's the reason why we wrote it like that. And what could be in this x beta? Well, in this 3 variable example, it is what? Exponential of what? Beta 0 plus beta 1 x1 plus beta 2 x2 and plus beta 3 x3. And it can be written like that, okay? Here, what I'm going to do is I want to change x3 by 1. That is, I'm going to increase the value of x3 by 1. Now I want to know what's going to happen. What's going to happen? So here, I want to know what's going to happen, right? So here, I increased the value of x3 by 1 unit. And how that's expressed in this, formula here? Well, basically, we increase x3 by 1, right? That's it. And we can expand the elements in this parenthesis, right? And, we can use the distributive law, right? So this becomes beta 3, x3, and beta 3. And already in one of my previous videos, I talk about, how the basic properties of exponential functions. And I'm not getting to that kind of basics, right? And next, what's going to happen? Okay, what I'm going to do is I'm going to take a ratio of these two expected rate or expected counts, right? So this is after we increase 1 unit for the variable x3. This is its initial status without that increase, right? Without that increase, that's its formula. And after its increase, it has additional term for what? E raised to the power of beta 3, or the exponential function, natural exponential function beta 3. So after we take that ratio, what's going to happen? Well, it's basically here, what we're going to say is that, we take a ratio and we get this extra term here. So once we take a ratio of these two expected counts, we get E raised to the power of 3. So in this case, what we're going to say, well, for each unit increase in x3, because we don't know where x3 starts and we don't know where x3 ends. What we do know is that x3 increases by 1 unit. And what's going to happen? Well, the expected count is going to change by a what? In this case, actually factor of E raised to power of beta 3. And the factor of xk, in this case, x3, does not depend on values of other x's, that is x1 or x2. That's a nice thing about this model. So to summarize and to generalize, so here we only use 3 independent variables. What if we have, 10, 20, 30? That's fine, right? So here we're going to generalize the interpretation here for x3 to xk, right? For xk. And in this case, we're going to say for a unit change in xk. Of course, in your homework or while working on some substantive project, we want to be very specific and go substantive about that unit change. So when we talk about education, we're going to say for a year increase or decrease, okay? Usually we say increase in education, okay? And note that here, we're not supposed to say for 1 year education, okay? We have to say in this case, for each year increase, that is change in education, okay? So in this case, we say, well, for a unit change in xk, the expected count changes by a factor of exponential function of beta k, or e raised to the power of beta k. So in our example is what? Beta 3 for x3. And we're going to say for, well, holding all other variables constant. Why can we say that? Because, while taking ratio of these two expected count, we cancel out, the inference of all other variables. The only thing that remains there is the coefficient for x3. When we generalize it to xk, you can try by yourself, going through the computation, right? It's going to be what? Beta k, okay? And in this case, if the exponential of beta k is greater than 1, we're going to say the expected count increases by a factor of e raised to the power of beta k. If exponential function beta k is a number between 0 and 1, well, we're going to say, well, the expected count changes, or actually it should be what? Decreases by a factor of e raised to the power of beta k, holding all other variables constant. Holding all other variables constant. So this is factor change interpretation of the results that you're going to use in your work.